Okay, then today we're going to look at Pythagorean Theorem. Yay! Now, Pythagorean Theorem is really nothing new for most of you. You've done this before. You looked at this probably back in 7th and 8th grade. You already learned a little bit about Pythagorean Theorem. We are going to take it kind of to a new level, because now we aren't going to have just nice whole number sides, although sometimes we will. For the most part, we will not. We will have more challenging side lengths, things like the square root of 17 or 2 root 3 or stuff like that. We all know that a squared plus b squared equals c squared for a right triangle. This only applies to right triangles. It only has applied to right triangles. But for a right triangle, a squared plus b squared equals c squared. This is literally what that means, drawn here. This is what the ancient Greeks were actually doing. What they said is the area of this square plus the area of square b equals the area of square c. That's what they're talking about when they came up with this. That those areas, the sum of the two smaller areas equals the area of the larger one. And the interesting thing is that works not only with squares, it also works with equilateral triangles. It works with semicircles. If I were to draw a semicircle with diameter A, and a semicircle with diameter B, and a semicircle with diameter C, the area of this semicircle plus the area of this semicircle would equal the area of that semicircle. But it's hard to write A semicircle plus B semicircle equals C semicircle. That doesn't work. Or area A equilateral triangle plus B equilateral triangle equals C equilateral triangle. That's not very useful for us mathematically. A squared plus B squared plus C squared makes the most sense, which is why we do it that way. But that's what Pythagorean Theorem is actually doing. It's not about squares and square roots and exponents, it's about area. That's what they were working with when they came up with this. So that's what we were working on. We weren't. I actually wasn't around with Pythagoras myself. A couple of years before my time. I wasn't smart enough to get into his school either. They kicked me out. But me and the ancient Greeks, togas, all that fun stuff. All right. So solving Pythagorean Theorem. Sometimes it's very simple. Sometimes it's very straightforward, and we get problems like this, and we just set it up. 5 squared plus 12 squared equals x squared. Now, biggest mistake people make in Pythagorean Theorem problems is losing exponents or trying to work too fast. Gosh, I said it yesterday. I'm going to say it again today. Slow down, show your work. The more steps you show, the fewer mistakes you will make. 5 squared is 25. 12 squared is not 24, it is 144. So x squared is 169. Of course, we solved that equation by taking the square root of both sides. So x equals, now technically, square root of 169 is 13. It would be positive or negative 13. We learned that in algebra. Because negative 13 squared and positive 13 squared both give me 169, don't they? We're not sure which one. But in geometry, we generally don't concern ourselves so much with the plus-minus issue or positive-negative issue because we're talking about a length. And since we don't have such a thing as negative length, the length of negative 13 doesn't make any sense to us. So we're only worried with the positive 13. So we're going to stick with just the positive. And we have the length is 13. Now notice that that makes up a right triangle, those side lengths, 5, 12, and 13. We call that 5, 12, 13. We call that a Pythagorean triple, because that's a set of 3 whole numbers, no decimals, no fractions, no anything like that, that for which a squared plus b squared equals c squared. And what we see is that triangle being used a lot. And it's useful to know the Pythagorean triple because it saves us some work when we have 5 and 12. Oh, we automatically know the hypotenuse is going to be 13. Because we know that 5, 12, 13 works. But we can always fall back if we don't remember that and actually do the little bit of math that's necessary to solve that. Very typical Pythagorean theorem problem. Little less typical. In fact, this is the one that more people will make mistakes on than anything else. Because they go 6 squared plus 10 squared equals n squared. Big rule about Pythagorean theorem. C is not always the unknown part. C is the hypotenuse. When we have a squared plus b squared equals c squared, A and B are legs of the right triangle. C must be the hypotenuse. And you should be familiar enough with what legs and hypotenuse are in a right triangle at this point. The legs are the two sides that make up the right angle. Hypotenuse is the long side, opposite the right angle. So in this case, when I set up my Pythagorean theorem, and by the way, A doesn't have to be the shortest and B the next longest and C the longest. A and B are interchangeable, but a lot of people go with A as the shortest side, B as the next longest side, C as the hypotenuse, just to keep it easy in their head, and that's fine. It's not a problem. Just realize A and B are interchangeable. So we'd say 6 squared plus n squared is 10 squared. And again, we expand that. And to subtraction, I get n squared is 64. So n is the square root of 64, which is 8. So Pythagorean theorem isn't always just taking whatever two numbers were given in the picture, squaring them and adding them together. Sometimes you have to subtract. You have to look at the picture and analyze the situation to decide how you're going to handle that. But again, notice we came up with nice whole numbers, 6, 8, 10. Another one of those Pythagorean triples. Nice whole numbers. Here's one that's kind of in multiple choice format. It was originally set up kind of as a quiz format question, but we can go ahead and do this. How would we set this up? Somebody tell me how you'd set up the equation in this case. What did you do?
7 squared plus y squared equals 69 squared.
Good. So 49 plus y squared is 81. Subtract the 49 from each side. I get y squared equals 32. So y is the square root of 32, which we now need to simplify. What perfect square goes into 32? What's the largest one? You don't have to look too far. What? 16, yeah. So 4 root 2. So right there. Now, let's take a look at this for a second as far as the way that we set up problems. What if I had done 81 plus 49? I'd have come up with 130, wouldn't I? Notice that answer is there in the distractors. When we look at a multiple choice question, whenever we have answers that are not the correct answer, those are called distractors. And again, this is set up so that you might pick the wrong one. Or if you switch the 2 and the 4 around, if you have a tendency to do that, C is there. 2 root 4 uses the same numbers, but in a slightly different way. If I subtracted wrong, I got 42 instead of 32. That's there. So you have to be very careful when we're looking at problems in multiple choice format to make sure we set it up correctly. Because one little mistake, and again, this happens when you're working quickly and in your head. You get the 49 and the 81, and people just add 49 and 81, 130. Oh, there's 130. They see that answer, they jump on it. But you didn't do the correct thing. You didn't set it up. You didn't do it the whole way. This is one other reason why we want to slow it down, write it out, work with it. Show our algebra all the time. That's how we want to handle this. How about this one? How are we going to set it up? Come on. Somebody tell me what to write. What you got? Yeah. Yeah. Not too hard to set up. And again, step by step. 4 squared is 16. 8 squared is 64. So it's 80 is z squared. So z is the square root of 80. Yeehaw! Oh, square root of 80 isn't up there. It has to be simplified. Which one of those same values is the square root of 80? Well, I guess the easiest way to do it is to figure out what perfect square goes into 80. 16 times what? 5, all right? Here 16 is 4 root 5. Is that up there? Aha. First answer. All set. So you're not just always going to get nice whole numbers. Sometimes you're going to get nasty things like that. And that's just kind of the way that it's going to go. Okay, again, some notes for you. Things that we notice. Number one, the hypotenuse C is not always the unknown side. We have to be careful where we put the variable. We have to be careful where we put our knowns and where the variable ends up. Second, because a squared plus b squared equals c squared, we cannot conclude that a plus b equals c. We cannot just take the square root of both sides of that equation. It does not work. Because we have that sum, a squared plus b squared, the square root of that is not a plus b. It doesn't work that way. Besides the fact of the algebra error, what keeps us from a plus b equals c for a triangle? What geometry concept from first semester? Anyone remember what geometry concept would prevent us from saying in a triangle that a plus b has to equal c? Remember back to the little demonstration that a lot of us did? I had this segment here, I had one segment over here, and another one over here, and they'd rotate around, okay? And we'd see where they touched. Remember that one? Those who were in my class, we did it on a sketch pad, but... And what do we conclude? That these two sides are not going to touch unless the sum of these two parts right here, a plus b, had to be greater than c in order to make a triangle. That was the triangle inequality theorem from first semester. So not only can we not take the square root of a squared plus b squared equals c squared and just say a plus b equals c because of algebra, we also can't do it because of geometry, because we know in a triangle a plus b always must be greater than c, where c is the longest side. The sum of the two shorter sides must be greater than the length of the longest side. That's always the case in a triangle. So don't make the mistake of just taking the square root of the sides when we do the Pythagorean theorem. You have to actually work with a squared, b squared, and c squared. And be careful not to lose those exponents. How do we use it? Pythagorean theorem is often used in things like this. Find the altitude of this right triangle. And from that, maybe find the area of this right triangle. Or isosceles triangle, excuse me. The triangle is isosceles, which means that these two sides are congruent. Okay, this side is congruent, and since isosceles, we know these base angles are congruent and that this is a right angle right here. So clearly by angle, angle, side, or angle, angle, side this way, those triangles have to be congruent. which means that this must be the midpoint of the side, so it's divided 3 and 3. That's special about isosceles triangles. If that's 3 and 3, what is the altitude here going to be? A, the altitude of the triangle, or the height of the triangle. How are we going to set that up to find that? What's the equation going to look like? You gotta let someone else answer. You're getting, you got it. I know you got it. I want other people to learn to talk in here. At least answer questions. It's not a bad thing. How am I going to set it up? What do you got, Micah? Yeah. Yeah.
I misspoke. I meant to say a square, but yeah, I got the right answer.
Okay.
Yeah, that's how it is. But like,
This is what you want.
that's what I want, but that's not what I said.
Oh, I thought that's what you said.
That's what I should have said.
Okay. Well, that's what you got, and it's right. So we just solved that out. Subtract the 9. And a squared is 55. So a is the square root of 55. Now, can we simplify the square root of 55? That one doesn't simplify for us. Simply, well, 5 and 11, that's true. 5 and 11 are factors of 55. Absolutely right. But neither of those are perfect squares. So it doesn't help me. So the altitude is root 55. So what would the area of this triangle be then? Use K for the area of the triangle. The area of the triangle is simply base times height divided by 2. My base is 6 times height divided by 2. And whatever the unit squared is for area. And then I could reduce the 6 and the 2 to give me 3 root 55 units squared. That'd be my area. My exact area for that triangle. And by the way, the formula area equals base times height divided by 2 for area of a triangle should be very much review for you, because we've done that quite a bit. This is definitely getting into a more of a level 3, level 4 problem. When we start asking for the area of the triangle, probably more of a level 4 problem. So we have to set up, first we got to find our right triangle, set it up and solve it, and then apply that information to another situation. How about this one? Find the area of this isosceles triangle. Very similar. It's isosceles. If this whole side is 30, how long is this piece right here? 15. So again, there's my height, or my altitude. So I set it up, a squared plus 15 squared is 17 squared. So a squared plus 225 is 289. We subtract the 225. 64 is a squared. So a is the square root of 64, which is simply 8. Happy days. Nice whole number. Now I find the area of the triangle, which would be base times height divided by 2. So that's 240 divided by 2, or 120 units squared. Whatever the unit would be, inches, centimeters, meters, miles, whatever. So a little more work to find the area, but something that's fairly doable, something you should be able to handle from a math standpoint. But again, that's taking the next step. That's pushing it up into like a level 4 problem. Okay, Pythagorean triples. We kind of talked about them briefly. And we're going to see this in the homework, but let me just kind of review Pythagorean triples again. The Pythagorean triple is a group of 3 whole numbers that for which a squared plus b squared equals c squared. Okay? Common Pythagorean triples are 3, 4, 5, because 3 squared plus 4 squared equals 5 squared. 5, 12, 13. 7, or 8, 15, 17. 7, 24, 25. Yes. 8, 15, 17, and 7, 24, 25. Those are common Pythagorean triples. For each one of those groups, the squares of the 2 smaller numbers added together equal the square of the third number. So 25 plus 144 is 169. If something's a Pythagorean triple, a multiple of it is also. So 6, 8, 10. We multiply everything there by 2, that's Pythagorean. Or 9, 12, 15, that's multiplying everything by 5 or by 3. 30, 40, 50 would be a Pythagorean triple. It's multiplying everything by 10. So if we do a constant multiples to all 3 numbers, we get another Pythagorean triple. One of the problems I'll have you working on today is I'll give you 2 sides of a Pythagorean triple. You have to find the third side. Now, whenever that happens, there are 2 possibilities. Maybe I gave you one of the legs in the hypotenuse. Maybe I gave you both legs. I don't know. You got to do a little bit of guess and checking to see which one works out. So let's say I had 15 and 25. Well, I've got one of 2 situations here. Either it's 15 and this is 25 and that's my unknown, or I have 15, 25, and this side is unknown. That's what that's telling me. I'm not sure which situation I have. So I solve both of them to see if either one or both give me Pythagorean triples. So if it's this way, it's x squared plus 15 squared is 25 squared. That's x squared plus 225 is 625. So x squared is 400. So x equals the square root of 400. Now, if that winds up being a whole number, we've got a Pythagorean triple, right? Winds up being anything that doesn't give me a perfect square, we don't have a Pythagorean triple. It's the square root of 400. 20. X equals, which is 20. So this is the case. Check the other one. 15 squared plus 25 squared is n squared. So that's 225 plus 625 is n squared. So n squared is 850. So n is the square root of 850, which is not a perfect square. It does not simplify. That is not a Pythagorean triple going that way. Okay? Yes, I could simplify square root of 850, but it is not going to give me a whole number. There's always going to be a radical portion of that. So again, basically we set up the 2 different situations, and there it is in pictures, here it is in words, same basic idea. In fact, exact same idea. That's how we find Pythagorean triples, given 2 of the 3 sides. And you'll be doing that. And yes, it is a little bit guess and checky. You actually have to, gee, is it like this? Run the numbers. Does it work? Nope. Go back, try the other ones. It's possible that both will work. It's possible that neither will work. Pythagorean triples. Okay, again, a little bit of algebra review. Squaring the radical. What if I give you a side that has, in fact, let's give you the practical purpose of this right now. This side is 5 root 6. This side is 13. Find the unknown. When we set up a Pythagorean theorem, we have to do 5 root 6 squared plus 13 squared is x squared. So we do have to know how to square that. Remembering, we do 5 squared, which is 25. Root 6 squared is 6, plus 169. 25 times 6 is 150, plus 169. So that would be 319. So x is the square root of 319 units long. And I don't know if there are any perfect squares that go into 319. I kind of don't think so. If that is a Pythagorean triangle. All right? So we're going to get answers like that. That's why we spent all that time yesterday working with radicals, because we are going to have to work with them and use them. Just a quick review. Simplifying square root of 150. What perfect square goes into 150? Largest one? 25. 25 times 6, so that's 5 root 6. Not 6 root 5. So again, none of this today is really that hard. Some of it is a little bit more challenging, but for the most part, if you just slow yourself down, take your time, and think about each step, it shouldn't be too tough. One more. How are we going to set this one up? Who hasn't talked too much yet today? You want to take a shot at setting this one up? You don't have to solve it, just set it up, yeah.
X squared plus b squared
There we go. Now we're going to have to do a little squaring here. 2 root 3 squared. Remember, that's 2 squared times root 3 squared, so that's 4 times 3, which is 12. And 4 squared is 16. We subtract 12. So I get x squared is 4, and that's easy. X must be 2. And there we are. So clearly knowing the Pythagorean theorem is going to be very important, and being able to apply it is going to be very important, but equally as important is going to be able to work with the ability to work with radicals. In fact, I can tell you, we've kind of created this benchmark yesterday. There are a lot of radicals on it. A couple where you just simply have to go in and simplify them, others that just show up in the problems. So yeah, you're going to struggle if you're not going to learn how to work with radicals. Some of you may want to rework on the worksheet after last night, realizing that you really didn't get the answers you thought you got, but you wrote something down just because that was matched the bottom of the sheet. Okay, that's good. You got a couple points, but it's going to hurt you when it comes to the test if you don't ask for help with that between now and then. So be sure you're asking for help when you get the opportunity, okay? Let's look at the assignments for today. There we go. It's out of your book, page 436, 3 through 27 odd, 31, 39, and 40. There's also 3 vocab terms due on note cards. So make up your little vocabulary flashcard. And make sure I'll be checking those tomorrow. 3 theorems from the chapter. Then we continue with some new stuff tomorrow. Review Thursday, and our first benchmark is already on Friday. So we're moving right along. And if you do not have your book with you right now, people from my class first semester know you should be bringing your book with you to class almost every day. Don't sit here now for the next few minutes and go, well, I don't have a book. I'm not the lending library for geometry books. You've been given one. You need to keep it with you so that you can work with it. If you say, well, it's too heavy for me to carry around, carry it between here and your locker. At home, you can use the online book. And if you don't know about the online book, now would be a good time to find out about it. It's just nice to have. This is the access code. There's a link to it on my webpage. It's the link to the book's website. Very useful to have the online book, but you need that code if you're going to use the online book. So there you are.